In this example problem, we're launching a ball from ground level upward at 23 meters per second. Our first question is, how high does the ball go? We want to determine the maximum height. So you should make a drawing of this, and try not to reveal everything here. The ball starts at ground level. We're going to call that y equals 0. It's at its maximum height here. We want to know what's the value of y. That'll be our maximum height variable. We do not know the time to go up to this maximum height. It's near the Earth, so we know the acceleration is minus 9.81 meters per second squared. Here's our original velocity in the y direction, 23 meters per second. When it's gone as high as it is going to go, it's temporarily at rest. For an instant, it's at rest. Its velocity is 0. Well, if you should review the kinematic equations if necessary, but there is a kinematic equation for uniform acceleration that does not have time as one of the variables. This is the equation we should use. It has the unknown we're searching for, the y, and all the rest of the variables have known values. So we start putting those in. Final velocity of 0. Initial velocity is 23. That has to be squared. Our acceleration, it's very important to put in the minus sign. I'm working this problem with the upward direction being the positive direction. So we do need to have a minus 9.81. And then the y are unknown on the right side. Y naught is 0, so that is dropped off. If we multiply 2 times 9.81, minus 9.81, and now we add this term to both sides, it'll add 0 on the right. It'll give us 19.62y on the left side. 23 squared is 529. Take a square root of that, and we get 27.0 approximately meters for the maximum height. It's a reasonable number. Roughly, this is 90 feet. We don't need to calculate it exactly, but roughly 3 feet per meter. This is roughly 30 meters, 90 feet. That's a reasonable height for an object going nearly 50 miles an hour. 23 meters per second would convert to nearly 50 miles an hour, approximately 50. Second question, how much time is required to get to this maximum height? Well, this is even an easier calculation, because we can use the first kinematic equation. The final y velocity is the initial y velocity plus acceleration in the y direction multiplied by the time to go up. We want to know what is the time. We have information on the other 3 variables, so we put those in. 0 for the final velocity, 23 meters per second, and this is positive. Minus 9.81 for the acceleration. We simply add 9.81t to both sides, then divide 23 by 9.81, and approximately 2.34 seconds is the time required to get to the top. What about going back down? Well, I'm going to draw a new picture here, and now I'm going to start the problem with the ball at this highest point, 27 meters above the ground. Is going to be y naught, and our final position would be y of 0. Then we have initial velocity of 0. The final velocity is unknown at this time. We're not going to take advantage of our knowledge of concepts of vertical motion with no air resistance. So let's say that's unknown. We're searching for the time to get down to the ground. Again, the acceleration is a negative. The third kinematic equation will allow us to solve for this. It does not have the final y velocity. Time is unknown, so if we pick one of the other kinematic equations, we might end up with one equation and 2 unknowns. Our final y position is 0. Our initial y position is plus 27. The initial y velocity is 0, so this will prevent this from becoming a full quadratic equation. We will not have t to the first power. We do not need to use quadratic formula. 1/2 times minus 9.81 and t squared. So if we divide 9.81 by 2, have the negative term over here on the right. If we add 4.905 t squared to both sides, we produce 4.905 t squared equals 27. divide 27 by 4.905, and t squared is 5.505. And approximately, the time going down is 2.35 seconds. 2.35 seconds. See if I can get that on the screen for you here. Notice that this is slightly different than the result above. This is just due to rounding errors. Just due to rounding errors. The 27.0 is not exact for the height, but it's close enough. Then the time to go up does equal the time to come down with no air resistance involved. Now, what's the speed of the ball just before it hits the ground? I'm not going to redraw the picture, but we want to know this final velocity, just the instant. We don't know the magnitude of the final velocity. We want to know the speed just before the ball hits the ground. Well, we can take advantage of what was just discovered about the time to go down and use this first kinematic equation. The final velocity is initial velocity plus acceleration times time. So minus 9.81 for the acceleration, 0 for the initial velocity. We just have to multiply these two numbers, and what we come up with is the y velocity just the instant before the ball hits the ground is minus 23.1 meters per second. The question asks for the speed. That's not velocity. Speed is the magnitude of velocity. So the speed is 23.1 meters per second. And speed does not have a plus or minus sign. Notice that this is somewhat in agreement with our starting condition. This ball started going upward at 23 meters per second, and it is true in free fall problems, vertical problems with no air resistance. The speed when we reach the launch point is equal to the speed that we launched with. The velocities are different. The launch velocity is positive. The final velocity, when we come back to the ground, is a negative number, but the speeds are the same, 23.1 meters per second. So you should review some more problems on your own for this, and ask your instructor if you have questions.